In this video, we study the bitwise XOR operator. In previous videos, we studied the logical NOT and AND operators. We now extend this study to the XOR operator. As for the AND operator, the XOR operator requires two operands. As before, we will call these the primary operand and the co-operand. We recall that for the 2-bit XOR, the output is 1 if and only if one of the two inputs is 1. We will now apply this for the single-bit and multi-bit cooperand. For the XOR operator, a single-bit operand acts as a controlled inverter. When the cooperand is 0, the primary operand is unaffected. When, however, the cooperand is 1, the primary operand is inverted. This controlled inverter can be applied to our data processing example or to the image processing example. With the multi-bit cooperand, we can specify which bits of the primary operand are to be inverted. In data processing, this process is called bit flipping. We select which bits to flip by applying 1s to the flip controller, leaving the others at 0. The XOR operator will then flip those attributes which have been selected for flipping, and leave the others unaffected. In image processing, this process is called selection inversion. Again, we can select which pixels to invert by applying 1s to the bit selection. Another use of the multi-bit XOR is as a comparator. Corresponding bits of the operands that are matched will yield a 0. Corresponding bits that are unmatched will yield a 1. As applies to data processing, this is essentially a data search. The user defines a particular profile as a search item. The XOR operator as a comparator performs the search. The similarity between the search item and each item of the database is indicated by the number of zeros present in each result. A result composed entirely of zeros indicates that the search item exactly matches the database item. In image processing, this process is called template matching. In this case, the search item is called a template. Once more, the comparator indicates the similarity between the template and each item of the database by the number of zeros in the output. Bitwise logic operators are important for the implementation of other arithmetic operations. For instance, the single-bit AND operator has a direct application in binary multiplication. This is because a number multiplied by 0 yields 0, and a number multiplied by 1 yields the number itself. The NOT or XOR operators can be used to calculate the ones complement of a binary number. We saw in an earlier video that finding the ones complement is the first step to negating a number in 2's complement representation. For this reason, bitwise operations are often performed as logic arithmetic. Hence, using hexadecimal representation, if A is the binary number represented by 37, and B is the binary number represented by 49, then, using the bitwise logic operators, A bar is the number represented by C8, and A and B is the number represented by 0, 1.